So, in the last session we have discussed about the concept of fugacity and its closure equation, and here first we will talk about how to calculate the fugacity using standard equation of state, maybe from this cubic equation or from this virial equation. So, you see that again, if I write, we know that ln phi I equal to 0 to p zi minus 1 dp by p. So, and its integration. So, if you break it down, actually it is an integration of v dp, right, because z is this pv by RT. So, it is v dp's integration. So, this form is not compatible for cubic equation of state, we have to change it, but before that this is quite compatible with virial equation. So, zi we know that it is 1 plus b prime into p, and in terms of this if we truncate the other terms, and it can be written as bp by RT into v, bp by RT, where b is the volume explicit forms coefficient, right, and it is a standard custom to write this pressure explicit forms coefficient to replace it by the respective volume explicit forms coefficient of virial equation. And actually you see that this is also 1 plus b by v. So, from there we get this. Okay. If I compare and replace this b prime, this p here as ZRT by v, and from there we will get this will be equal to, from comparison, this bp by RT. So, you see that we will discuss later the z, regarding the dependence of z. We have 3 parameter, we will discuss this later, 3 parameter theory of corresponding states. Which states that Zi is a function of reduced pressure, reduced temperature and eccentric factor. And PR, the reduced pressure, is pressure by critical pressure, TR is also the same. Just for the time being, noted an eccentric factor is the species specific constant, right. The physical meaning and all will be discussed when we study this equation of state. So, here in order to corroborate with this 3 parameter theory of corresponding states, we write that this to be BPC by RTC into PR by TR, right. So, we can write that, and this BPC by RTC we write as B naught plus omega I B1. How it is coming and everything, we will discuss it later. So, this B naught and B1, see, if I separate out, this becomes a form which is perfectly in this corroboration with 3 parameter theory, which can be expressed like this, right. So, this part is Z1 and this is entirely Z0, and from the experimental data, this B naught and B1, they can be determined as a function of TR, and You do not have to remember this equation, but just for calculations I am giving it. B0 equal to 0.083 minus 0.422 divided by TR to the power 1.6, and B1 is equal to 0.139 minus 0.172 TR to the power 4.2. So, according to this equation we can calculate provided we know this eccentric factor. Now, if I am going to use this ln phi I and this equation, this zi minus 1 you see is 0 to p b naught plus omega I b1 into pr by tr, right, into dp by p, which we can change to dpr by pr because pc in the differential and pc in the denominator will cancel out. So, this pr cancels out and we get b naught into pr by tr plus omega I b1 pr by tr, right. So, there is further we can write this as ln of phi I 0 plus omega I into ln of phi I 1. This is, we are trying to match the mathematical form, and from there we can write this phi I equal to phi I 0 into this phi I 1 to the power omega I. So, in a way what I am trying to demonstrate that we can exactly calculate this ln phi I using the virial equation of state. Now, you see this dressing the closure equation for cubic US, cubic equation of state. Right, we have to mathematically manipulate and change this form from VDP to PDV, because if you look into this cubic US, the typical one is van der Waals. Van der Waals equation. So, it is P is equal to RT divided by V minus B minus A by V square. So, pressure is expressed as a function of volume. So, the integral from VDP change to integral of PDV for cubic US, right. So, you have to replace this. So, you see this ln phi I 0 to p, z is PV by RT minus 1 dP by P. So, this dP we are going to replace, and how we can replace? We know that d of PV is equal to PDV plus VDP. So, d of PV minus PDV divided by V equal to dP. So, if you do that 0 to p, or let us not put the limit right now, PV by RT minus 1 d of PV minus PDV divided by P and V giving you PV. So, here that pressure equal to 0 to pressure, this state So, we will change it to volume as well, we will see it. So, what about the first term? PV PV d of PV by RT, right, first term. Next term, PP cancels out dV by V. So, minus P by RT dV minus d of PV by PV, and then minus minus plus dV by V. Now, let us decide about the individual limits of 4 integral. So, the first, P equal to 0, the ideal gas state. So, for ideal gas, when P equal to 0, PV equal to RT, and here it is PV. Now, P by RT dV, so this is V infinity ideal gas volume at a given pressure to V. This is again RT to PV, this is again V infinity to V. So, if I do it, it will be PV minus RT divided by RT, the first term. The next term, V infinity to V, we have to keep it as it is. We cannot integrate in general unless the equation of state is supplied. The next is minus of ln PV by RT, which is Z, plus ln of V by V infinity. So, this is PV by RT Z, or let us write Zi, Zi minus 1 minus V infinity to V, P by RT dV minus ln Zi, and this you see numerator and denominator we can multiply by P. So, PV becomes, it will be just as it is, and PV infinity is RT. So, this is a plus ln Zi. So, these two terms cancels out. So, finally, we have the equation ln phi I equal to Zi minus 1 minus V infinity to V, P by RT dV. So, that is my working equation to find out the fugacity coefficient for pure species using cubic equation of state. So, let us take again the example of van der Waals equation. And let us solve it. See, specifically we have to solve P by RT. So, what is that? This is given here, P by RT is equal to P by RT equal to 1 divided by V minus B minus 1 by RT A by V square dV. So, from V infinity to V. So, this is becoming V minus B divided by V infinity minus B minus 1 by RT. This will be minus of A by V, minus of A by V upon integral. So, A by V infinity minus A by V, right. Now, you see this V infinity is much larger than V itself. So, this term in the denominator we can neglect it and can write V minus B divided by V infinity. Minus 1 by RT here it will be plus A by V. Okay. So, this V infinity is again RT by P. So, you can substitute it here and we can write P into V minus B divided by RT plus 1 by RT A by V. So ln phi I according to van der Waals is this expression Zi minus 1 minus ln of p v minus b divided by RT plus 1 by RT a by v square. Now solve v from known p and t using van der Waals cubic equation of state, and once you know v, next you calculate Zi as PV by RT and substitute it here, you will get the answer for a specific problem. So we have and we can use, we will see later that once these other cubic equations are introduced like Redlich-Wang, Swaff-Redlich-Wang, Peng-Robinson, etc. So there also we can use this same equation and can solve for this pure species fugacity coefficient. Next we will discuss about how to find the fugacity of a compressed liquid. Fugacity of a compressed liquid. Now you see at saturation Gi V is equal to GIL, right, at saturation, because just we have studied at phase change there is no change of Gibbs energy. So GIR equal to GIRL equal to GIRV, right, and we call it GIR sat. So at saturation both the liquid and the vapor they have the same residual Gibbs energy, that means the same fugacity coefficient, which is RT ln phi I sat, right. So phi I sat we know, or alternatively it is, we can also write RT ln phi sat by P sat. This is a P sat is a saturation pressure. Now we want to calculate the compressed liquid fugacity. Now what is the state? See, we have P sat T, saturated liquid, and we are going to P and T compressed liquid at the same temperature. Right. So you know that we have dGi is equal to VI L liquid volume into dP at constant temperature. So this dGi, on the other hand, if I integrate now, it is Gi, or rather its dGi is equal to RT d ln Fi, that we can write. So VIL dP. So integrating it will yield RT ln Fi by Fi sat, and on this side VIL P minus Pi sat, the saturation pressure. This will be Pi sat. So the ratio of the compressed liquid fugacity to the saturation fugacity becomes exponential of VIL P minus Pi sat by RT. And this exponential term entirely is called Poynting factor. after the name of the scientist, Henry Poynting, who actually proposed this compressed liquid fugacity concept. Now, if I sat, you see, directly we cannot calculate, we calculate phi I sat, as it here that phi I sat into p I sat will be equal to f I sat. So, further we can write that f I is equal to phi I sat into p I sat into exponential of VIL p minus p I sat by RT. So, that is the final foolproof relation for this compressed liquid fugacity through Poynting factor. Okay? So, this is the compressed liquid fugacity. So, next we will now going to introduce this idea of component species fugacity. Now, see what is the overall framework for this single component fugacity what we have discussed right now or discussed in the previous session, that we have started from pure species ideal gas, and from there keeping the mathematical relation intact, keeping the dependent variable same, we have changed the independent variable from pressure to fugacity. So, here first we will try to formulate the partial molar Gibbs energy or chemical potentials expression in terms of pressure related pressure in terms of pressure basically for ideal gas mixture, and after that we will extend this expression, extend the idea of the theoretical framework of this expression to real gas mixture. So, topic is this component species fugacity for real gases. So, we have to discuss component species fugacity. Now, for an ideal gas mixture, from Gibbs theorem you see is Gi bar Ig is equal to Gi Ig plus RT ln Xi. We have solved it using Gibbs theorem. So, at constant temperature dGi bar Ig is equal to dGi Ig plus RT d ln Xi. Now, for pure, this is for pure species, for pure ideal gas we know that dGi Ig is equal to RT d ln P at the same constant temperature. So, we replace it and we get dGi bar Ig equal to RT d ln P plus RT d ln Xi, resulting RT d ln Pxi, right. Let us say this is equation 1. Now, we will extend the same equation for real gas, and note that previously for pure species it was pressure, now it is partial pressure. So, it is quite consistent, the mathematical form is quite consistent. Here it was the pure species Gibbs energy, and for this gas mixture, ideal gas mixture, it is the component species Gibbs energy or partial molar Gibbs energy of the component species, which is nothing but the chemical potential. So, you can write it as d mu I Ig as well. So, for real gases, gas mixtures, we will keep the same mathematical form. So, dGi bar, so RT d ln, but we are going to change the independent variable. Now, instead of pure species fugacity, now it is component species fugacity, where Fi cap is the component species fugacity. Right. So, once we have introduced this component species fugacity definition, again we have to go for a closure. So, let us say this is equation 2. Now, we know Gi bar R partial molar residual Gibbs energy equal to Gi bar minus Gi bar Ig. So, automatically if you take the differential dGi bar R equal to dGi bar minus dGi bar Ig at constant temperature maybe, right. So, once we are imposing the constraint of constant temperature, so dGi bar becomes consistent with these expressions as given in 1 and 2. So, RT dln Fi cap minus RT dln Xip, right. So, dGi bar R RT dln Fi cap by Xip, and that term we write as dln phi I cap at constant temperature. So, you integrate it, you will get that Gi bar R by RT equal to ln phi I cap plus a constant, say Bit, right, which is dependent on temperature, and on the species, but it does not depend on the fact that whether it is real or ideal gas mixture. Now, for if we apply the same equation for ideal gas mixture, Gi bar R equal to 0 and phi I cap equal to 1. So, this Bit equal to 0. Now, what is to be noted that we have at constant temperature Gi bar R by RT equal to ln phi I cap. So, if you just write the equation ngr del ni at Tp Nj I naught equal to j 1 by RT equal to ln phi I cap, right. So, as temperature is constant, we can include this RT in the derivative itself. So, del of ngr by RT del ni at Tp Nj I naught equal to j equal to ln phi I cap. So, what we understand that ln phi I cap and not phi I cap is a partial molar property. This entire thing is a partial molar property. Now, as it is a partial molar property, it must satisfy this summability and Gibbs to M. So, number 1 summability Gr by RT equal to summation Xi into Gir bar by RT. So, Gr by RT is Xi ln phi I cap, right. Second, Gibbs to M at constant temperature and pressure. We know Xi into Gir bar by RT, d of that, sorry, so essentially we have Xi ln phi I cap equal to 0. At constant temperature and pressure. Now, with this, now we will try to just like fundamental property relation for U, G, A and H, we will try to derive what is a fundamental property relation for GR by RT, normalized residual Gibbs energy of a mixture. You see, already we have established that d of NGR by NG by RT equal to NV by RT dP minus NH by RT square dt plus summation del of Ng by RT del Ni at Tp Nj I not equal to J dni I equal to 1 to n, right, for real gas mixture. Now, similarly we can write for ideal gas mixture as d of Ngig by RT Nvig by RT minus Nhig by RT square dt plus summation I equal to 1 to n del of Ngig by RT del Ni at Tp Nj constant I not equal to J dni. So, if you subtract these two, what you will get? Upon subtraction, we get d of Ngr by RT Nvr by RT dP, sorry, here dP will be there, dP minus Nhr by RT square dt plus summation of del of Ngr by RT del Ni at Tp Nj I not equal to J dni I equal to 1 to n. So, this is nothing but ln phi I cap. So, we have d of Ngr by RT equal to Nvr by RT dP minus Nhr by RT square dt plus I equal to 1 to n ln phi I cap dni, and this relation is called fundamental residual property relation. And here from actually we can solve for a very important quantity, which is how ln phi I cap changes with temperature and pressure. See, this term can be written as del del P of Ngr by RT at constant temperature and Ni, which is Nbr by RT. Now, we operate it with del del Ni and this outer derivative has got the condition Tp Nj constant I not equal to J. So, if we take the derivative of this term with respect to Ni, it will be Vi bar R by RT, partial molar residual volume. So, now if I interchange the order of the derivative, del del P here, del del Ni here, and the condition will also flip. So, we can write del of ln phi I cap del P is equal to VIR by RT. And similarly, del of ln phi I cap del T equal to minus of Hi bar R by RT square. So, that is about the different properties of this phi I cap. So, we have started from we have started from this definition and we have established the first principle definition here, and from there we have concluded that ln phi I cap is a partial molar property, not phi I cap singly. So, it satisfies summability and Gibbs duhem. From there we have solved for this fundamental residual property relationship, and also from this fundamental residual property relationship that how this phi I cap is changing with pressure and temperature. That has been solved. Okay. So, next finally we have to move towards the closure, because similar to phi I, that is the pure species fugacity coefficient, here also we have to solve for component species fugacity coefficient, some measurement protocol, how we can in real life, how we can measure this component species fugacity coefficient. So, it is the closure of ln phi I cap, right. Now, you see the mixture, a gas mixture can be considered as a pseudo pure species, just like we can say that here is a pseudo pure species which has got a molecular weight of 29 around, right. So, we may write Gr by RT equal to 0 to P Z minus 1 dP by P for a mixture as well, considering it as a pseudo pure species, right. So, we will multiply both sides. This is not the pure species, it is a pseudo pure species, it is valid for a mixture. So, multiply both sides by n, which is the total number of moles. Now, if we take the derivative with respect to Ni at constant temperature, pressure and Nj, this becomes ln phi I cap, and on this side it becomes and this is what? Partial molar compressibility factor. So, ln phi I cap equal to 0 to P Zi bar minus 1, the form, mathematical form of this previous closure equation for pure species also being retained, right. Now, with this equation, we will try to solve it using the same virial equation, that Z is equal to 1 plus dP by RT, right. However, here B is B mix. Now, let us consider a binary system for simplicity. We will extend it for multi-component. So, for a binary system, B mix, it is equal to the mixing rule for virial coefficient. We will discuss it again when we study this equation of state. The mixing rule for the second virial coefficient is summation over I, summation over j, bij, yi, yj, right. So, okay, if it is not for a binary system, for the mixing rule for second virial coefficient. Now, for a binary system, B mix or B, let us write B is B mix and same. So, it is y1 square B11 pure species 1's B plus y1 y2 B12 plus y2 y1 B21 plus y2 square B22. Now, B12 and B21 they are same, 1-2 interaction and 2-1 interaction, that same. So, obviously B12 and B21 must be same. So, B is equal to y1 square B11 plus 2 y1 y2 B12 plus y2 square B22. Now, what we will do? We will try to get rid of this pure quadratic term, that is y1 square and y2 square. So, y1 square how will you write? We will write y1 square as y1 into 1 minus y2, okay, and similarly y2 square as y2 into 1 minus y1. So, it is a simple mathematical manipulation. So, B is equal to y1 into 1 minus y2 into B11 plus 2 B12, just to get a relatively simple mathematical form. We are doing this. See how it will actually be helpful. y1 B11 plus y2 B22 plus 2 B12 minus B11 minus B22 into y1 y2. Right. So, this is y1 B11 y2 B22 and let us write delta 1 to y1 y2, where delta ij is equal to 2 bij minus bii minus bjj, and you note that delta ij equal to delta ji, they are same, right, because b12 equal to b21. So, that is B. So, if I use this equation here, what I will get? So, Z is equal to 1 plus Bp by RT for a mixture. So, Nz is equal to N plus Nb into P by RT. So, del N1, let us say we are trying to find out phi 1 cap. So, del N1 of del of Nz del N1 at Tp N2 is equal to 1 plus P by RT del of Nb del N1 at Tp N2, right. So, this is basically Z1 bar. So, ln of phi 1 cap 0 to P Z1 bar minus 1 dP by P. So, if I substitute this Z1 bar minus 1, so it is 0 to P by RT del of Nb del N1 at constant Tp N2 into dP by P. So, P cancels out. So, we get upon integration P by RT del of Nb del N1 at Tp N2, that is ln phi 1 cap. So, we have to find out this derivative when we have this mixing rule, right. So, if I have this mixing rule and we have simplified it for binary system. So, let us solve for del N1 of Nb at constant temperature, pressure and N2. So, we have B is equal to y1 B11 plus y2 B22 plus delta 1 2 B1 delta 1 2 into y1 y2. So, Nb is equal to N1 B11 plus N2 B22 plus delta 1 2 N1 N2 into N, as yi equal to ni by n, and n is equal to summation of ni. So, it is that. So, if I take the derivative nb with respect to n1 at Tp n2. So, it is b11, this is 0, and delta 1 to n2, denominator n square, here n minus n1. So, this is b11 plus delta 1 to n2 square by n square, b11 plus delta 1 to y2 square. Therefore, see, if we substitute this expression here, ln phi 1 cap becomes p by RT b11 plus delta 1 2 into y2 square. Similarly, ln phi 2 cap is p by RT b22 plus delta 21 y1 square. Now, if this is for binary system, how to calculate this b11, b12 and b22 we will discuss later, just after this. Okay. So, if I think of now a ternary solution, right, where the compositions are y1, y2 and y3, see, then the B mix, this principle will remain same, and finally the expression is this. So, we have to calculate this, and we have to change the mixing rule, or so not the mixing rule, the expression rather. So, it is summation I equal to 1 to 3 for ternary system. Ij equal to 1 to 3, Bij, Yi, Yj. So, it will be B11 y1 square, B12 y1 y2, B13 y1 y3 plus B21 y2 y1, B22 y2 square, B23 y2 y3 plus B31 y3 y1, B32 y3 y2 plus B33 y3 square. Now, see, this y1 square we can write as y1 into 1 minus y1 minus y3, sorry, y2 minus y3. This y2 square we will write y2 into 1 minus y1 minus y3, and this y3 square we will write as 1 minus y2 into y3 into 1 minus y2 minus y1. So, we are getting rid of this pure quadratic term. So, we will get a similar type of expression, but it will involve delta 1 2, delta 1 3 and delta 2 3, right. So, from there we have to solve it, and we can further extend it for quaternary systems and all. So, if we solve it for ternary system and quaternary system, for multi-component mixture, applying the principle of induction, we will get ln phi k cap equal to P by RT BKK plus summation yi equal to 1 to n, j equal to 1 to n, yi yj 2 delta ik minus delta ij, something like that. Let me check it out. And multiplied by half only, right, and that we can solve by the principle of induction. So, you see this delta ik and delta ij, we can get as delta ik equal to 2 bik minus bii minus bkk. Now, next and the last question is how to solve for these bii and bij, the pure and for this mixed second virial coefficient. How to get the measures of bii and bij. So, you see for pure species bii, right, it is B0 plus omega I B1, right, B0 plus omega I B1, and we know this, we have already discussed that B0 is some A1 minus B1 divided by TR to the power 1.6 and B1 is equal to A1 prime minus B1 prime divided by TR to the power 4.2. So, you know the critical temperature of the specific component I, and from there we will get this TR, and there from B0 and B1, and knowing the eccentric factor we can calculate bii. That is a pure second order, the second virial coefficient. Now, for mixed bij, this is exactly not the case. It should be bii into P divided by RT, right, because Bp by RT was equal to B naught plus omega B1. So, it will be bii into P divided by RT is this. So, bii can be calculated from here. So, bij is equal to, or PCTC, sorry, or PCI TCI. So, bij is by induction, by the similitude, it was suggested that it should be R TCij divided by PCij into B naught plus omega ij B1. So, what is the mixing rule? Mixing rule suggested by Brownitz what is that? Here omega ij is simply considered this arithmetic mean. Okay. TCij is yij or rather yes, TCI into TCj, TCI into TCj, yeah, to the power half into 1 minus Kij. This Kij is called binary interaction parameter. It is an adjustable parameter. So, that value will be provided, binary interaction parameter, right. If its value is not available, we can drop it. And ZCij, though it is not used, but in order to calculate this PCij we have to use it, is ZCi plus ZCj by 2, and PCij is ZCij R TCij by VCij, and VCij equal to VCi to the power 1/3 plus Vcj to the power 1/3 half whole cube. So, it is some kind of intermolecular distance at the critical state, because Vci to the power 1/3 is a length dimension and it is equivalent, it is in the order of, it is the order of this intermolecular separation at this critical point for the component I. Similar is for J, and for the mixed state it will be some arithmetic mean. So, from there it has been calculated. So, you see that these are the mixing rules suggested. So, mixing rules are empirical, but it gives a very good estimate of ln phi I cap, because based on this accuracy of this estimation of Bij, we will have the actually the accuracy of ln phi k cap or phi 1 cap, phi 2 cap in case of a binary system. So, this is the closure and the demonstrative example for the calculation of component species Fugacity coefficient. And again, I must say that there are equations or this change of this form, that here we have used what? Here we have used this form, right. So, it is compatible, the form is compatible with virial equation. But if I have to use the cubic equation of state, we can further change it and go for mathematical expression very similar to the pure species, which is compatible to gas mixtures cubic equation of state. But that is beyond our scope here, at least for GET. I do teach it in this regular semester course, but here I am not going to discuss it. Okay? So, that is all about this Fugacity and first phase of the solution thermodynamics. But it is very important to understand finally, that will be my concluding remark about all this analysis. It is mathematically complex and integrated, and it requires rigorous practice to actually grasp the essence of this specific topic which I have covered. So, the thing is, why we are studying this? What is the point of studying solution thermodynamics in chemical engineering? Right. See, we know that dgi bar equal to RT dln Fi cap. Now, if we consider an equilibrium relation, consider any equilibrium, that is vapor liquid equilibrium, solid liquid equilibrium, liquid liquid equilibrium and solid vapor equilibrium, right, out of which the vapor liquid equilibrium is the most commonly used or most commonly explored phenomena in chemical engineering. As you know, in distillation, this liquid liquid equilibrium, we use it in liquid liquid extraction, and there we have to predict this. In distillation, in solving the problems of distillation, we have to predict this equilibrium relation, just like relative volatility. So, here the point is, at equilibrium, Gi bar, let us say it is vapor and this is liquid, that will be same. So, dgi bar vapor equal to dgi bar liquid. So, at constant temperature RT, because the equilibrium must be at constant temperature, RT dln Fi cap V equal to RT dln Fi cap L. So, obviously, we can conclude that equilibrium, the Fugacity coefficients must be same, right. So, question is, so far see V, so far in this phi I cap and the closure equation of phi I cap, we have solved, we have discussed that how to calculate the component species Fugacity coefficient in the vapor phase, right, because here the reference state is an ideal gas mixture and the respective property is a residual property. From there we are able to calculate this Fi cap V. But Fi cap L I will discuss in the next session, and it comes via the model of this ideal solution, and therefrom the deviation has been accounted in terms of excess property and subsequently this activity coefficient. And there are also closure, multiple closure, because there is no standard equation for the closure of activity coefficient. These are called the activity coefficient or excess Gibbs energy models, right. So, from there we will be able to predict this Fi cap L, the component species fugacity in the liquid phase. And now once we have the expressions, once we have just like this expression is now phi I cap yi into P. And I know how to calculate the phi I cap at least using this method. So, once we know this expression and we will be able to, and once we are able to calculate, once we have studied the liquid phase and the liquid solution and the reference, taking the reference of ideal solution, I will discuss what is ideal solution later in the next session. So, from there we will be able to get this expression also. So, we can generate the equilibrium relations of vapor liquid system. And similarly, we can extend the idea for liquid, solid vapor system. Definitely, I am not going to discuss all of it. We will discuss this vapor liquid equilibrium and liquid equilibrium. And finally, we will pass on to understand this reaction equilibrium. So, that is the entire scope of the solution thermodynamics as well, or solution and reaction thermodynamics, which is the specific to chemical engineering. No other engineering discipline specifically focus on this. They mostly study this engineering thermodynamics. Definitely in physical chemistry, they focus on this type of expressions and they are bothered about this equilibrium relation. But these equilibrium relations are very, very important in chemical process design, because the size of this distillation column, size of this liquid extractor, or the solid liquid means it's leaching, right. So, they all depends on this equilibrium relation. We can check the feasibility of whether the distillation or the separation by distillation is possible or not, a liquid extraction whether it is possible or not, that we can actually understand upon checking the equilibrium relation. So, that is why the thermodynamics and this process, this chemical engineering, this solution thermodynamics is so important in process design. Thank you.